Okay, so let's start. Today we are going to learn about test oracles, which is an important component for writing tests. And this is today's outline. So we will be go through the overview of test oracles, like the definition, like the difficulties of designing test oracles. And then we will learn three different groups or three different families of test oracles. Four different families of test oracles. And before we jump into the definition of test oracle, let's recall what we have learned. So in our last lecture in the test scaffolding part, we have learned this. So this is the entirety of a test scaffold, right? And we know that this can help us to execute the target program unit. And we have already, in the previous weeks, we have already learned how do we generate a large amount of test inputs, right, with different black box or white box techniques. We know how to generate these test inputs. And we know that with the test scaffolding technique, we can automatically collect some test outputs by executing the test inputs. But how do we know that whether the output is correct or not? It requires some sort of output comparison. And we briefly mentioned this. This output comparison thing is known as test oracles, theoretically. So today we are going to learn this in detail, like how can we systematically check whether the output of the program is correct or not. So inside this example unit test, can you identify which is the test oracle? So the tool asserts these are the test oracles. And we will learn about this in detail today. So that's just a brief impression of what is test oracle. And now let's have a formal definition of test oracle. So we know that tests are like just sequences of inputs and outputs. So it's like a mapping between different inputs and outputs. And the question is, we have learned how do we generate these inputs, like using different techniques, and we have learned how do we execute the program automatically to get these outputs. But what we don't know is, we don't know what is the expected output and how should we construct this. And this expected output is known as the test oracle here. So basically, test oracle is just a predicate that can give us a verdict of whether a test pass or fail. So this is the definition of test oracle. So it is just a predicate to tell whether a test is a pass or fail according to the relationship between the actual output and the expected output. So this is the definition of test oracle, which is quite straightforward. I'm talking about oracles, we may think of this, right, like fortune telling kind of thing, like predicting the future. So because it's like predicting something, so it's actually a predicate here. And we have learned that in the second lecture of verification versus validation, we learned that if we want to do some kind of verification, we need to verify the implementation according to some specifications or requirements. And for validation, for testing here, we are actually checking the implementation against the test oracles, right? So you may think, okay, we are in verification, we are checking the implementation against specification. Here, we are checking the implementation against Oracle. So what's the relationship between like specifications and Oracle here? So are they the same or are they not the same? What do you think? So they are actually not the same here. So on the one hand, Oracle is so we can build oracles based on specifications. So which means that Oracle is like a specification is more like a high-level description of the expected behavior of the program, and the Oracle is the actual check that we implement in the test case. So we can derive test oracles according to the specifications. And on the other hand, we can say that, okay, a specification is not inherently automatically becomes an oracle, right? So we may need to concretize the specification to make it a test oracle. So this is the relationship here. So we can think of it as like specifications are more high-level, abstract description of the program behaviors, and oracles are like low-level, concrete descriptions or checks for the expected behaviors. So this is the difference here. So they are not the same, although they can serve for similar purposes. So oracles are actually the mechanism used during testing, and specifications are written normally before testing. So this is the difference. And test oracle is made up of basically two components. So we can see that the first one is oracle information. So this is to use for describing the correct implementation. So it's more like describing the specification in the oracle. So this is oracle information. And the other one is oracle procedure, which means that, so this one is more like the description of the expected behavior, the expected output of the program. And the second component is oracle procedure. Oracle procedure is more like how do we validate this expected behavior against the actual behavior we observed from the test input. So this oracle procedure could be very straightforward, right? Could be as easy as just an equality check here. So we can just check whether the expected output is the same as the actual output we get. So, and you can see here, the expected output is actually the oracle information here, right? So the procedure is just this check. And we know that oracles are different from specifications. And we know that oracles can have oracle information, can have oracle procedure. So essentially, oracles are just like yet another piece of code. We can implement it as a piece of code. So which means that oracles must be developed somehow by the developer or tester, right? And this lead to some consequences. So it means that the oracle, since it is developed by the developer, like other functions, like other program features, it may contain faults. And faulty oracles could be troublesome because it may lead to false positives where the test oracle tells us it's a fail. This test fails when there's no actual fault in the program, and this is false positive. And there could be false negatives where the test oracle just tells us that this test has passed when there is actually a fault in the system. So faulty oracles, because oracles need to be developed by humans, So faulty oracles could be troublesome. And we need to somehow think about how can we ensure the quality of the oracle, right, as a piece of software. So we need to somehow verify, like how we verify code, like general software or program. We also need to verify oracles. So we can like we can perform verification and validation for oracles. And we can even like write tests for oracles. And then this becomes a circularity problem. So we use oracles to, as part of the test, to test the program. And then we develop the test for this test, right? And then do we need to develop another test to test the test of our test? So this becomes a circularity problem. So in the end, we cannot like loop all the way, like stacking the tests here. So what we need to do normally is that we just make sure that we do a very lightweight verification for test oracles normally. So like for example, we at least do a manual code review for test oracles. But then the problem is how do we like review or how do we verify the test oracle, right? How do we do this lightweight verification? We need to have some metrics to measure the quality of test oracles, right? In order to do this verification. So before we jump into the measurements or metrics for measuring the quality of test oracles, let's think about this design issue. Let's think about why it is hard, sometimes hard to design and verify test oracles. So we know that it's easy to come up with new inputs. For example, if let's assume that we have implemented this Fibonacci function which calculates the Fibonacci value given the position of that value. So we can easily come up with the test inputs 1, 10, and 100, right? It's very easy. But it's much harder to generate the expected output. Like for example, it's somehow easy to generate like the expected output for 1 or maybe even 10. But what about 100? It's hard to actually know this expected output beforehand, right? So most commonly, so the developers are actually writing these oracles by hand, and then all these test oracles are tied to a specific test case, especially according to the test input. And then this means that it requires a large amount of effort and time, right? Because if we don't implement this function, we need to calculate this with some other means. Like we need to calculate the expected output with some other means by hand or use some other programs to calculate the expected output. And since this is mostly a manual effort, so it is very error prone and it is very hard to verify the correctness. So it's all about putting a lot of effort. Unfortunately, we do have some low effort approaches for developing this, and we will learn about it later today. And we just need to know that, okay, this is it's a tedious process to design and develop test oracles. So we must know some simple approaches for evaluating its quality. And since sorry, what's going on? Since we may devote huge effort to develop test oracles to generate the expected outputs, we may need to think of some trade-offs to save our effort to design test oracles that are good enough. So like how we design software. So what we do is because test oracles require us, like what we have seen in the previous slide, it requires us to specify the output behavior, right, in a very concrete way. It's not like a descriptions. We need some concrete values. So what we can do is we need to save our effort. We need to balance between different properties here. So what we can do is we can, for example, we can trade precision for general reality. So which means that we can specify the properties that should be obeyed by a function by building a model of the function, rather than specifying the concrete value. We can use a model to abstract away the behavior of the program and use the model to cover multiple different concrete values, right? So this is some this is like a trade-off here. So you can see, for example, we can normally when a function returns 0, it means that this function is succeeded. For some APIs, we know that if it returns 200, then 200 something, then it's a success. So instead of like checking the actual, like maybe the output of the function, like whether this function has calculated Fibonacci correctly or not, we check whether this function is crashing or not, is looping infinitely or not. So these are so in this way, we are not catching some specific bugs. So we are not precise, but we are kind of generalized, right? We don't care about the details. So we can do some trade-offs. But this is like a very high level trade-off. So can we think about some actual properties that we need to balance for these test oracles? So there are several properties related to test oracles. So, and there are basically three concepts here. So a test oracle is complete if it can offer a verdict of any set of test input. So this means that it is very general. So every test input could be checked by this oracle. Then this oracle is considered as complete. And the test oracle is sound if it's guaranteed to offer the correct or the right verdict for any test case that it claims to be able to support. So this is sound. So we can imagine that the checking for whether a function is crashing or not is a complete test oracle. And it's also a sound verb or oracle, right? Because if a program crashes, then it means that there must be something wrong with the program. So it's both sound and complete. And we say a test oracle is correct if it is both sound and complete. And we call it partially correct if it is sound but not complete. So, like for example, if we check the assertions we saw on the scaffolding slide, they are actually partially correct, right? They can cover the exact test cases, but they are not complete. They cannot cover all the potential test inputs. So now let's come back to how can we, since we have learned how these properties, so let's come back to how can we use these properties to judge the test oracles. So what we can do is we can use the cost to build these oracles. So it's like how much effort do we need to build a test oracle? Like, because sometimes we have to derive the expected output by hand. So it could be very costly to build, and we want low cost for building test oracles. And we can also track the accuracy of the verdicts, like whether a program crashes or not is not a very accurate verdict, right? Because we don't know what's triggering the crash. We just know that the program is wrong, but we don't know why it is wrong. So it's not accurate, but it's low cost. And for accuracy, we want high accuracy. And then for completeness, we want high completeness, right? We want the test oracle to be usable to cover as many test inputs as possible. So we want high completeness. And those are the properties we can use for judging the quality of a test oracle. And there are many different types of test oracles according to how they are derived. How can we derive them? So the first one is specified oracle. So specified oracles are the type of oracles which are written by the developers. So this is the first type. The second type of oracles is called derived oracles. So these type of oracles could be automatically generated according to the program. So this is the second type. And the last type is known as implicit oracles. So this type of oracles are the oracles which should be satisfied by almost all programs, and which doesn't even require us to derive them. For example, whether a program crashes or not is an implicit oracle. So we don't need to like derive that a program shouldn't crash from the code of the program, right? We know that every program shouldn't crash. So so crashing is like an implicit oracle. And then we can also fall back to human as oracles. So we can allow humans to decide whether the output of a program is acceptable or not. So as we can see, the specified oracles are the most accurate ones. So these specified oracles are most accurate. And human oracles, of course, they are also very accurate. And implicit oracles are not very accurate, but they cost much less. So we can see, because specified oracles requires developers to write them, and derived oracles could be automatically generated, and the implicit oracles don't even need to be generated. So the cost is dropping, but the accuracy is also dropping here. So we will learn about it in detail later. So that's all about the overview of test oracles. So we have just learned the definition. So it is just a predicate to tell whether a test passes or fails. And we know that it has several properties that needs to be balanced to save the effort for developing them. And we also know that we can have 4 different types of oracles according to how we generate them. So the first family of oracles we're going to learn is specified oracles. So specified oracles are like, as indicated by the name, are specified by humans. So they judge the program behavior using a human created specification of correctness. So this is a typical workflow of applying these specified oracles. So what we do is we create the expected output according to the test input we create, and then we use it to compare with the actual output of the program. So this is the specified oracles. And most of the oracles we have seen until now are actually specified oracles. So most of the manually written test cases we have seen right now are have a specified oracle. For example, here in this unit test. So this is like the assertion here, the asserts here are actually the specified oracles. So we specify the expected value here. So it's not coming out of nowhere automatically, right? It's actually calculated by the developer. So it's specified by the developer. So it's known as specified oracle. So most of the oracles we have seen here are specified ones. And there are actually some subtypes of specified oracles. So the first one is expected value oracles. So it's actually the simplest type of oracle. So we just specify the value according to the input. So for example, here we have the max function as the test, and what we do is we just, and according to the input 3 and 7, we specify the expected output as 7 for this max function, and then we compare the two values here. So this is the expected value oracle. And as we can see here, this type of oracle is closely related to the test input, the value of the test input in the test case, right? So we need to specify the expected output according to the input we have. So this type of oracles are usually not reusable. So because if we change the input value here, this expected output may also need to change. So it is often not reusable. So we need to think about how can we extend this to cover multiple test cases, right? But we will cover that later on in some other types of oracles. But here, this one, it doesn't generalize, so it lacks completeness. And another type of oracles is known as self-checks within the functions. So just now we are for the expected value of oracle, we are actually trying to specify the expected output of a function. So the oracle is created outside the function. Now, for the self-check, it means that instead of creating the oracle or the check outside the target function, during development, we can inject some checks inside the function itself. So this is the structure of the self-check as oracle. So you can see the difference. So the difference is that for expected output, for the expected output oracle, the expected output is the check is created, is done outside the program. And the output is created according to the test input, right? It is not very complete because it cannot be used for multiple different inputs. But if we inject some checks within the function, the target function itself, then we don't need to care about what kind of input we receive, right? If we can inject the checks properly. So in this case, these self-checks can be applied for multiple different inputs, and it's kind of decoupled from the inputs. So it's more complete. So normally it can also take the form of assertion. So this is an example. So for example, we are implementing a multiply function here. So this multiply function could be as simple as just the result equals to A times B. So what we can do is, instead of returning the value directly, we can insert some self-checks. For example, if any of the operands, if any of the operands here is 0, then the result must also be 0, right? So this is a self-check. So in this case, it doesn't matter. So the check is not coupled with any input. So we just need to check whether there are like assertion fails or about signals after the program executes, right? So this type of check is more complete because we don't need to create one test oracle per test input. So this is more generalized. But as we can see here, we are also trading off accuracy. So we are not, if let's say we implement this as a plus b, wrongly, we implemented this function wrongly as a plus b, then we may still, then these checks may not help us to capture the bug here, right? Because they are not accurate. They don't check the actual value of C. So we are actually sacrificing accuracy for completeness here. So this is like self-check as oracles. And here are some general guidelines for us to design these self-checks. So normally we should write these self-checks at the function level. So within a function, we add some asserts to check for some internal properties of this function. And if we can like come up with some self-check that could be applied to any input, then that's the best case here, right? Because the purpose of doing self-checks is to make it applicable to more inputs. So this helps us to increase the completeness. And there are some limitations of these self-checks because they are only accurate for those checked properties. Like we have seen just now, if we wrongly implemented the times as a plus, then we may miss some thoughts because it's not so accurate. So we are trading off accuracy for completeness here. And apart from like using a specific expected value and inserting some self-checks to check some internal properties of a function, what we can do is we can also try to use some system level of models as oracles too. So it's like levels of testing. We also have levels of oracles. So we can have system level of oracles. So in lecture 10, we learned system testing, and for system testing, we learned model-based testing. And model-based testing requires us to create a model to describe the behavior of the program. And we know that you can hear the keywords, we are describing some behaviors of the program, right? So why can't we just use the description of the program behaviors as a checker to check the correctness here? So we can actually use these models as an indicator of correctness. So in this case, we are using these system models as oracles. For example, we have learned equivalence class. We have learned the decision table, which is actually a model for describing the program behaviors, right? And in the decision tables, we can actually use the actions related to the test inputs as a test oracle here. So this action is a test oracle. And sometimes if we model the system as a state machine, we can have some error states. And if the program enters the error state, then we know that there is an error of the program. So we can also use system models as oracles here. But we know that all these three types of oracles are all written by the developers here, right? So they are known as specified oracles. They can't be like somehow automatically derived, right? Even for decision tables, for models, we have to somehow manually model these systems. So these are like manually created oracles. And if we want to save our effort, we can also try to derive some test oracles automatically from the program we are testing. And these type of oracles are known as derived oracles. And we have several approaches for deriving test oracles. So here is like a description of this. So we can actually derive test oracles based on the existing sources of information. And most of the time, the existing sources of information is just the program we have, right? The program we are trying to test. So normally we can use documents, existing tests, and other versions of the same system. So we can also try to observe this information from program executions, and we can try to detect some invariants. We can also try to mine some specifications automatically. And the first actual technique for deriving test oracles is known as differential testing. So this definition is a little bit overwhelming, so let me explain it to you. So differential testing, as indicated by the name, is that we are trying to differentiate the result values from multiple versions of program doing the same task. So for example, if we are trying to test a PDF parser, we are trying to test the behavior of a PDF parser, what can we do? What we can do is we can get another PDF parser and execute both our target PDF parser and the other PDF parser together with the same PDF file and see if they can give us the same result or not. If they cannot give us the same result, it means that at least one of them is wrong, right? Most of the time, at least one of them is wrong. So, like for example, if we have like maybe another example is like we want to test the slide, the PPTX file parser. So what we can do is we can try to render the PPTX file inside this Google slide. We can also try to open it in PowerPoint. And if they look differently, the same file looks different in the two systems, then it's very likely that one of them is wrong. So that's the spirit. So instead of like manually specifying what is correct and what is wrong, we just compare the results of the different systems doing the same thing. And if the results are different, then one of them is wrong. At least one of them is wrong. Maybe both of them are wrong, right? So this is the purpose of differential testing. So once we know that, then the steps are kind of straightforward. So what we do is, the first step is we need to select some variants. We need to select some candidates for us to test against, right? We need to select multiple targets, multiple programs doing the same task. So this is the first step. The second step is we need to generate some test inputs. And this test input generation could be done with some random testing techniques like fuzz testing. We will be learning this later. And then we execute the variants, the different programs doing this same task with the same test input. And then we compare the results and see if there are any differences or not. So this is basically the steps. And actually, you may think that, okay, this is very straightforward. This is like kind of very simple. But actually, in practice, sometimes it could be very hard to compare just the final output. Because most of the time, like if we see just now we were using the example of rendering the slides, so we can visually see the differences. But sometimes the program may just return 0 or 1, like for example, some command line interface tools, they just return 0, 1 or some status code, right? Then we cannot see what's happening inside, even if they return the same output, final output, there could be still some errors. So we need to sometimes we need to inject the program to capture some internal behaviors and compare the results. And this is very hard. So we can do some research here. So this is differential testing. And another technique for deriving test oracles is known as regression testing. So you may have heard about this before. So the key purpose of regression test is to make sure that the new features regression testing is normally done during the development. So sometimes in most of the cases, we are not developing all the features at once, right? We are developing maybe the first prototype, and then we add some new features to the prototype. And how do we know that the newly added feature doesn't break the existing, doesn't affect the performance of the existing functionalities we have already implemented? Then this needs regression testing. So regression testing is to actually just create a test case, a test suite, and then run our program on this test suite and observe the outcomes of the program at that state. And then we add a new feature to the program and run this test suite again and see if the new output is worse than the previous one or not. So the previous output is kind of automatically serving as the test oracle here, right? The output of the previous version of the program automatically becomes the test oracle. So this is the spirit of regression testing. It's just to test whether the new features introduces new issues or regressions of existing functionalities. So that's why it is called regression testing. So the older version of the program, or the older version, the output of the older version of the program is automatically the oracle here. So this is regression testing. So it's more like a differential testing done on different versions of the same program. It's kind of like that. And then yet another technique here is known as metamorphic testing. So although they are like called testing, like differential testing, regression testing, metamorphic testing, they are actually not about how do we design test cases. They are about how do we derive test oracles here, right? So another technique we can use for automatically deriving test cases is known as metamorphic testing. And this metamorphic testing is a relatively new technique, although it's like 20 something years old, but it's I think it's 27 and or 28. So, but it's still considered as a relatively new technique here. And it was proposed by T.Y. Chen, and basically this guy. So here's a backstory of this technique. So, and this guy is actually currently a professor still here. He's not retired. So he's a professor in Swinburne University. And like many other valuable research, like deep learning, you know, that deep learning, when it was firstly proposed, like all the machine learning and AI community is like resisting, like fighting against the deep learning people. So like many other like valuable research, metamorphic testing was not recognized by the academia when it was firstly invented. And actually, this is a screenshot from the paper, the first version of the paper. And this is the guy, the direction, this guy. And he did this, I think, when he was a visiting scholar in Hong Kong University of Science and Technology. So you can see that it's published in an internal journal of the university, not even like published beyond the university. So, and it's published in 1998. So it's like 28 years from now. So it's older than all of you, I think. But yeah, but it's still a new technique. So, so this is like the backstory of this. And but actually this is a great research, and it actually starts an entirely new direction for software testing, which is just known as metamorphic testing. So let's see why it is a good technique. So this is the definition, which is again very long and kind of boring. So the key idea of this is that this metamorphic testing is used for solving the cases where it is hard to or impossible to get the exact value of the expected output. So this is the problem we are trying to solve with metamorphic testing. So in the cases where we don't know how do we get the expected output, we can try to use this metamorphic testing technique. So why it can do this? Because we are trying to identify some metamorphic relations between the inputs, between different inputs and different outputs of the program, and try to use these relations to derive test oracles. So we are trying to use these metamorphic relations. So this is still quite abstract. You may think, oh, what is like a possible metamorphic relation, right? We can see an example later. And we can transform the input data according to the metamorphic relation and compare the result. Because metamorphic relation can give us the relations between different inputs and different outputs. And we can create different test inputs according to these relations and compare their outputs. We can actually try to guess the correctness of the execution of the program. So this is the key here, as you can see. So you may wonder, okay, what is a metamorphic relation? Why it can work here, right? So let's see an example. And remember, we are sacrificing precision for generality here again. So let's see why. So let's assume that we have implemented a function to calculate the value of sine x. So it's very hard to get the expected result, right? So what's the result of sine 1? It's hard to calculate. And it actually, if we want to get the exact result, we may need to get the exact value of pi here, right? And sometimes, and we know that we can never get a truly precise value of pi, right? We cannot. So it's hard to get the expected values here. So how do we create test oracles to see if this function is implemented correctly or not? So here we need to come up with some metamorphic relations. I don't know why it's popping up again, but yeah, let's come back. So, so the metamorphic relation here is sine x equals to sine pi minus x. So what we can do is, if we design a test input 1, then we use, because pi is like a number of the math library for most of the languages we are using right now. So then we can use pi minus 1 as the second input and see if the program generates the same output. Instead of checking whether the output is correct or not, whether sine 1 is correct or not, against some expected values, we don't calculate the expected value here. We just check whether sine 1 equals to sine pi minus 1. If the results are not equal, then this function is likely to be implemented wrongly, right? If the results are equal, then this function is likely to be correct. We can't say it is correct because cosine pi also equals to cosine pi minus x, right? Cosine x. So we are actually sacrificing the precision for the completeness. So you can see here we can do the input data transformation according to the metamorphic relation we can get. Right? We can get. So you also notice the sacrifice of precision, right? Because we can only verify, we can only tell whether an implementation is wrong or not, but we cannot fully prove that this implementation is correct or not. So this is the metamorphic relation. So you can see to get this kind of relation, you may need some domain knowledge. Like here, you need some domain knowledge about math. In some other cases, you may need some other domain knowledge. So this is metamorphic testing. And before we do this exercise, let's have a 10 minutes break. And let's do this exercise and see if you can remember the concept you just learned or not after 10 minutes. So I'll see you at 8 past 5. Let's have a break.
It's a closest human if all these three depends. I know that cost of lower dollars and or risk to I guess it's lower. Yeah, right. Plus completeness. Completeness is like growing. Because this one is applied for type. Yeah, like because like a company crashes if a program crashes, then it's a signal for our programs to be passing errors. That includes every false readings. Yeah, because the program shouldn't be crashing for error for any input. So that's why it's very common. And for derived purpose, it's similar example for different testing. Maybe for regression testing, every software, almost every software has like multiple versions. So we can always do regression testing for softwares. So it's also quite complete. Just by developers. So for the regression, as far as there's some disability change, like the standing analysis, like for new functions we introduce, sensible and so forth. Regression, yeah, it actually helps if you can do some like control the volume of the analysis to see if there are like relations between the feature and it's going to help us to narrow down the scope and these kind of techniques. It depends on this static analysis technique. Well, yes, contents since the relations tables, yeah, to help teams or groups. Yeah, yeah. You took 6 months to revise this one. Oh, I see. That's why. Yeah, that's out later. Yeah. What's for verification?
For verification,
For verification, if you like directly prove that something is correct. Yeah. Spec.
yeah. But for verification, it's not really long. Even there are some like tools that can help you to do this, but
I don't think you can fully automatically do this without very strong AI.
like now we have smart AI which can help us to do verification, but I don't think it's really automated.
I'm curious, I also learned like things. Definitely.
Oh, so you learned.
Yeah, I think there's a new incoming actual tutors family. Good. So it's also part of the it's the first thing very different. It's
Yeah, it's
complicated. Yeah, it is complicated. And it is also something.
Okay, so let's continue to the exercise. So as we can see here, deriving these metamorphic relations is not a very easy task. It requires some insights. It requires some domain knowledge. And let's try to evaluate some like metamorphic relations. So let's assume that we are trying to test a function that sorts an array of numbers from min to max. So and this basically this function accepts an array as inputs and returns the sorted array. So which of the following metamorphic relations are valid? So the first one is if the input array is reversed and passed to the sort function, the output should be the same as the original array sorted. The second one is if an identical element is added to the array, the output should maintain the other but include the additional element in the appropriate position, like which means that duplication is allowed and duplicated elements are not merged, in this case, by this sort function. And the appropriate position means that the duplicated element is in the this ID plus or minus one of the original element. So this is the second metamorphic relation. The third one is if the array is sorted and concatenated with another sorted array, where all elements are larger than the original one, then sorting the combined array will give us the same result as sorting them separately and combining them together. So which of the metamorphic relations are valid? Okay, I think some of you have already got the answer. So let's see. Okay, good. So it seems that most of you have kind of chosen all three. So actually all of them are valid. All of them are valid. Let's see why. So let's assume that we have this array 5, 1, 4, 2, 3. So the first metamorphic relation is if we reverse the array and pass it to the sort function, then we should get the same result as the original sorted array, right? So this is pretty much a valid metamorphic relation. This is very straightforward because, and this is called a metamorphic relation because we don't really specify the expected output, right? We don't know what's the expected output for as the sorted array, as the result for sorting this specific input value, right? We don't need to specify that. We just need to check whether the reversed array is sorted as is sorted the same as the original one. So this is a valid metamorphic relation. And the second one is if we insert an identical element, then it shouldn't be merged. So which means that what we can do is we can add a random, we can duplicate a random element here, and then this duplicated value should appear twice, shouldn't be merged. So this is also a valid behavior of the sorting function here. So it means that we don't accidentally merge values during sorting. So sometimes if we don't implement this properly, we may accidentally deduplicate elements. So this is also a correct check. And the last one is like this. So if we have another array whose elements are larger than all the values here in the original array, we sort the combined array and will give us the same result as combining the sorted array. So this should also be a correct behavior, right? So this is also the that is also a valid metamorphic rule. So as you can see, metamorphic rules are sort of like descriptions of the correct behavior of the program, regardless of specific values of the output. So as far as the description of the function's behavior is correct, then it could be used as it doesn't require us to actually calculate the output value. Then it is a correct metamorphic relation. So this is the case. And you can imagine that we can generate a lot of metamorphic relations for a given function. It's just how accurate it is. So some metamorphic relations can give us some accurate results, some are less accurate, right? So how can we generate more accurate metamorphic relations? How can we automatically generate these metamorphic relations are actually something that needs to be researched. So that's why this metamorphic testing is not just a single idea, it is like a direction of research. So that's why. Let's continue. So we have another technique for deriving these test oracles, which is known as invariant detection. So finally, something that is not named as testing, right? So this is invariant detection. We have actually encountered this invariant keyword somewhere in our previous lectures. Can you remember that? Maybe we'll have a recall in this slide. So invariant, let's have a quick recall of what is invariant. The invariant is a property or condition that is always true during the program execution. So that's very simple. So this is, of course, this is a formal definition, but you can imagine as invariant as just like something that is always true, no matter how we execute the program. So that's why it is called invariant. It's not changing according to the inputs. So the invariant actually we encountered is like loop invariant when we learn the light box testing, structural testing techniques. We encounter loop invariants. So loop invariance means that the condition is always true after every iteration of a loop. So this is called loop invariant. And we have encountered this down here. You can click on this link and see that slide. So, and we also have method of function invariants. So they are just like properties that are always true during the execution of this function. And we can see that because these values should always be true, so they are actually naturally, they could be used as test oracles naturally, right? If we observe them to be false during the program execution, then it definitely means that there is something wrong with the program. So this is called invariant detection-based test oracle. And there are actually some algorithms for us to detect these type of invariants. So for example, we can create a set of test cases that the program is known to produce correct behavior for, and then these test cases are just and then we observe these the behaviors by running these always like correct tests, and we can see the values, which values are not changed in the inside this during this execution. So those values are likely to be the invariants. So that's the case here. So we just create this is one of the simplest approach for detecting invariants, but there are actually detecting invariants determining which values or which conditions are invariants is a very, very hard problem. But this one is one of the easiest ones to derive invariants empirically. And we know that invariants could be used as test oracles naturally, right? And that's all about derived oracles. And now let's learn about implicit oracles. We can see that we are lowering the costs along the way, right? Because specified oracles requires developers to specify values, and derived oracles could be somehow automatically derived. And for implicit oracles, which means these oracles don't even need to be derived. They are like by nature, they are like the natural behaviors that all programs should follow. So implicit oracles, actually, they don't require any domain knowledge or specification. So they are like the rules or behaviors that should be followed by any program. For example, there shouldn't be some network issues or there shouldn't be crashes, and the program shouldn't have a deadlock, like running forever for something, right? And these are like, we don't even need to specify any output to derive this. And we don't even need to like compare it with other programs, right? Like how we do differential, like how we do regression testing. So these oracles are just the natural behaviors that programs should follow. So that's why they are called implicit oracles. We don't need to specify them. We don't need to tell what's right or wrong. And how do we capture this, or how do we force this implicit oracle? Most of the time, we can use sanitizers to increase the detection sensitivity. The reason is that sometimes these implicit oracles, although they are like easy to, they are very easy to like derive, or we don't even need to derive them, right? But the hard thing is sometimes they are hard to observe. Like for example, sometimes even if the program is implemented wrongly, the program may not crash. Even if the wrongly implemented part is executed, the program may not crash. So it's because we are not sensitive enough to trigger the crash. It's not about how we run the program. We will see an example later. And sometimes for that long, it's the same. So we don't know whether the program is stacking or it just takes it a longer time to execute, right? So we don't know. We need to be sensitive enough to use these implicit oracles. And one of the most used technique is known as sanitizers. So they can use these sanitizers to improve the sensitivity. And one of the most famous sanitizer is known as address sanitizer, or ASAN. So it is a compiler and runtime technique that can help us to find to trigger the bugs with zero false positives. So these are all the bugs that could be, all the different types of bugs that could be captured by a address sanitizer. You don't need to remember all of them, but you just need to know that they are all memory errors because indicated by the name address. So it's sanitizing memory addresses. So it's used for capturing memory-related bugs. So I believe you know what is a memory, right? You know, like pointers and memories. So the basic mechanism of this is that we, so, so you all know like malloc and free, right? Malloc is to assign a piece of memory to a pointer, and free is to free that piece of memory from the pointer. So what the program does, what address center does is it actually injects, it replaces the default malloc and free so that the memory addresses near the allocated memory are marked as red zone. So, or dangerous zones. So once these dangerous zones are like written or read by the program, then it can be detected. So that's the case. And once the memory is freed, then it is kind of disposed. So it shouldn't be used again. So if a piece of memory is freed, but it is used again, then we can capture that behavior. So this is roughly how it works. And although you think, okay, this is very tedious, it can capture so many bugs, and the basic mechanism is like, oh, it's still not so basic, but it's very easy to use. So this address sanitizer is designed to be very easy to use. So you just need to add a flag in your compiler to use it. So you just need to add this flag to use it. And let's see a report of this address sanitizer. So if it captures a bug, it will print out a report in the screen. And you can see you can clearly see some useful information from here. So you can see that the first piece of information tells us that this bug is a global buffer overflow, which means that it is a buffer overflow for a global variable. And the second piece of information you can see here is write of size 4. It means that there were 4 bytes stored outside the user-defined variable. And you can see that the third piece of memory is the information is that we can even locate the error in the source file if we compile the program with debugging information. So it can also tell us, okay, this error took place in this main function here of this file at line 7. So this is information. And the first piece of information is that this is the function, the original memory of the variable is allocated here in this line 3, and column 8. It can even narrow down to the specific column. And you can check more details about how our address sanitizer works in these two by checking these two links. And now let's see how address sanitizer works by showing you a demo here. If you are using a MacBook or a Linux system, you can follow me. So you can just copy paste the content of this file into a C file. So you can see here this font size. So in this C file, what we do is we try to allocate an array of 5 integers. So we try to build an array of 5 integers, and we initialize this array with some integer values, and then we try to read from this array. So the first one is we read the last element, because the index start from 0, so index 4 is like the 5th element. So this one is to access the last element, which is a correct behavior of using the pointer of the array, right? But if we try to read the integer of index 6, then it is the behavior of the program should be it's wrong, right? Because we are reading one more integer after what we have allocated for this array. So it's a wrong behavior here. So it's like reading, sorry, this is not 1 byte beyond the allocated, it's actually 1 integer beyond the allocated memory. Normally it's 4 bytes. So we are reading out of the bound in this case. We are reading out of the bound. And let's see if we just compile this program normally. So let me remove the compile files. Oh, sorry, I typed the wrong command. So let's see if there are any things here again. So I removed the compiled binaries, and let's try to compile them again. So let's try to compile the raw binary without address sanitizer. And then let's try to compile this with address sanitizer. You can see the difference here. I think we are just adding one more flag. There's no other tricks. We just add one more flag. And then we compile it. So now we have 2 binaries compiled here. One is the original, and the other one is the hardened binary with address sanitizer. So you can see if we run the original program, it doesn't crash. So it will print out the 5th element, which is the correct value, right? The 5th element is 40, and it will read an out of bound value. And this part of memory is not initialized at all. It depends on your system's behavior. So sometimes it could be a random integer, sometimes it's just 0, because it's not initialized. So we know that, okay, this program won't, we can't see the crash here, right? Even if it's wrong and we have executed this wrong statement, it doesn't crash, we cannot observe. But if we just run this and this hardened binary, then this is going to pop up. So you can see the report of from the address sanitizer. So you can see it is a heap-based partial overflow because for mallocs, we are allocating memories on heaps. And we know that this is a read of size 4, which means that it's reading. So this one here is wrong. It's reading 1 integer beyond, which is 4 bytes. So we are reading 4 bytes beyond the array. And because we didn't compile the binary with with debugging information, so it cannot give us the source information here. If we compile it with the dash G compiler flag, then we can get this result. But in general, you can see that the basic idea is just to show you that, okay, we can use sanitizers to harden our program to capture the potential bugs which are normally not observable. And that's the implicit oracle. So we can use, and of course, apart from address sanitizer, there are many other different types of sanitizers. And normally they are used during the compilation phase. So like UB sanitizer, like which is undefined behavior sanitizers, or some other different types of sanitizers. So that's the case for implicit oracles. And now let's come to human oracles. So just now, all the previous oracles, they are kind of like because we learned that oracles are made up of two components, oracle information and oracle procedure. So oracle information is more about the description of the expected value or expected behavior. And oracle procedure is how do we validate the oracle information, right? And just now, all the three different types of oracles, for all of them, the oracle procedure could be programmatically verified, right? We can write the entire oracle as a piece of code and then verify them. But sometimes it's hard to automate. It's even hard to automate the execution of these oracles or the checking of these oracles. For example, like we just mentioned, like whether the slides are rendered correctly or not. It requires some visual checking, right? Without some like humans but now we can use large language models, of course, with like large vision language models. But previously, without these kind of things, we have to involve humans to check for correctness. So that's why we can always fall back to use humans as the judge for checking the output. So, and sometimes the customers are like the final humans to find the bugs. That's the most unfortunate case. And of course, in the last few years, humans oracles are very popular for large language models because when OpenAI first released the GPT-3 or GPT-4 series, they use human feedback to help train the model, or do alignment with the model for the models. So in this case, we have to involve humans as oracles. And to do human-based oracle, it requires like a lot of human effort or manpower. So what we can do is we can outsource the oracle problems to use many human oracles in some platforms. And here are some like popular services that we can use. Like the most famous one is Amazon Mechanical Turk. So we can use this. So we can always try to outsource the human oracle effort. And also related to AI, the most recent case is Scale AI, which is a company for providing human label data to all these other companies. And I guess maybe you know this guy, Alexander Wang, and he's like, he joined Meta and caused a lot of drama there. So this is the case. But yeah, this is like another example of human oracles. So human oracles are used for like AI nowadays. So although you may think that, okay, human oracles may not be so good for software, but they are actually very useful for AI nowadays. So that's all for today's lecture. And before we end this lecture, and let's have a quick recap of what we have learned. And you can try to recall the concepts as I go through them. So today we have learned the concept of test oracles. So like an oracle is like related to predictions, right? So for a test oracle, it is used as a predicate to tell whether a test case is a pass or a fail. So this is the definition of test oracle. And for test oracles, they are normally made up of two parts, the oracle information and the oracle procedure. And sometimes we may need to use humans to run this procedure here, right? But most of the time we can write a piece of code to run this oracle procedure. And for these oracles, because most of the time they have to derive it, they cannot fully automatically derive these test oracles. So we have to somehow devote some effort to create these oracles. And because we would like to save our effort for creating these oracles, we have to balance different properties like the cost, like the accuracy, like completeness. So with these properties in mind, we have a taxonomy of different oracles here, right? We have 4 different types of oracles. We have specified oracles, we have derived oracles, we have implicit oracles, and hidden oracles. So for specified oracles, as indicated by the name, they are specified by the developers. And the most common and simple specified oracle is to use an expected value. Right? We can write an expected value for some input and use it to check whether the output of the function or the program equals to the expected value. So that's the first type of specified oracle. But because expected values are like paired with inputs, we want to create some test oracles that are not paired with inputs to be more complete. Then what we can do is we can try to inject some check-ins in the target function or the target program we are trying to test. And then we can get the self-checks as oracles. And that's the specified oracle. And of course, we can also try to, if we move on to the system level, we can also try to use different system models to provide guidance to work as specified oracles. So that's about specified oracles. And for derived oracles, we can automatically derive some test oracles using some existing like resources we have. And we have learned actually 4 different types of techniques for deriving test oracles. The first one is differential testing. So as indicated by the name, we are trying to differentiate the outcomes or results of different variations or different variants of programs doing the same task. If they behave differently when doing the same task, then at least one of them is wrong, right? So that's the differential testing. And for regression testing, it's more like a simplified description about regression testing is to do a differential testing between different versions of the same program. And we also learned metamorphic testing. So metamorphic testing is used for solving the problem where it is very hard to generate or to predict the expected output of the program. So instead of trying to capture the expected output of the program, what we are trying to do is we try to identify some metamorphic relations of the target program using our domain knowledge, right? And use these metamorphic relations to generate test inputs. So, and a metamorphic relation is like a correct description of the program behavior, which doesn't involve like predicting any expected output. So we can create many metamorphic relations for programs. And apart from these three techniques, we also learned the invariant as the oracles, right? So we can try to identify invariants inside the program and use these invariants as test oracles. And one practical usage of invariants actually I didn't mention in the slide is actually there are a lot of invariant-based testing done in Web3 industry. Because smart contracts, there are certainly some very important invariants. Like you don't want hackers to drain your pool of tokens, something like that. So invariant is also very practically useful technique. And apart from derived oracles, we also have implicit oracles, which are like the behaviors that must be followed by all the programs. So because these behaviors are some behaviors that must be followed by all the programs, we don't need to devote any effort to derive them. So the key is about how sensitive we are when observing for the behaviors, right? So to increase sensitivity, what we can often do is to use some sanitizers. And a typical example here is address sanitizer. And then lastly, we just, and before that, we can see that for all these three oracles, three types of oracles here, we are from top to bottom, we are having increasing completeness, and we have lower cost, we have lower accuracy, right? So because the last one is almost cost-free, as you can see, we just need to add a flag when compiling the program. So these are the properties of these different types of oracles, and of course, we can always fall back to humans as oracles. And maybe traditionally for software, human oracles are not so useful. But now, since we have large language models, we need to do alignments. We need to align their outputs according to human values. So human oracles are getting more and more popular nowadays. So that's all for today's lecture. And thank you for coming.